Now that we have seen various properties of the Lorenz transformation coefficient matrix as well as the definition of the Poincare transformation, let us take a look at the group structure underlying this. So we are now looking at the Poincare group. The Poincare transformations, remember, are x prime mu equals lambda mu nu x nu plus a mu, or you can rewrite this in shorthand as x prime equals lambda x plus a Lorenz transformation on x followed by a translation. We can show that two such transformations carried out one after the other is actually going to be a Poincare transformation once again. That's pretty easy to see. You start with x mu goes to x prime mu is one transformation under the bunch of parameters given by lambda and a. So x goes over to x prime under this transformation which we denote by these numbers. Then we have another transformation lambda bar a bar which takes x prime to x double prime. In terms of components, this becomes x double prime mu is lambda bar mu nu x prime nu plus a bar mu. But x prime nu is already the result of one Poincare transformation, that is lambda nu sigma or lambda nu rho x rho plus a nu plus a bar mu. So you have lambda bar mu nu lambda nu rho x rho plus lambda bar mu nu a nu plus a bar mu. Note that this is nothing but the product of the two matrices lambda bar lambdas, mu rhoth element, x rho. This thing is actually the muth component of lambda bar a plus a bar. So what we see is that this transformation that we have here, which takes x to x prime using lambda a and x prime to x double prime using lambda bar a bar, is effectively the same transformation that you can carry out in one go using the parameters lambda bar lambda and lambda bar a plus a bar. And this means that the transformations that are induced on physical states, which we denote by T of lambda A, must obey the following property: T lambda bar A bar, T lambda A, which means first carry out this Poincare transformation, then carry out this one, must be the same as T of lambda bar lambda and lambda bar A plus A bar. Of course, we still really should check one thing, which is this: are these consistent with a Poincare transformation? Lambda bar A plus A bar is nothing but just a column vector or a bunch of 4 numbers. That stands for translation, no problems there. We should really check whether lambda bar lambda, the product of two Lorenz transformation matrices, is a Lorenz transformation matrix. The way to check that is simply this. Remember, a Lorenz transformation matrix L would obey L transpose eta L equals eta. So here we have L bar transpose eta L bar, the matrix corresponding to lambda bar, is also eta. Both of these are Lorenz transformations. And so what we need to check is L bar L, the product. Does that actually satisfy the basic demand that every Lorenz transformation should satisfy? So we should check this. Now this, of course, is L transpose L bar transpose eta L bar L, and because of the associativity property of matrix multiplication, you can rewrite this as L bar transpose eta L bar. That is, just change the position of the brackets without changing, of course, the order in which the matrices occur. Now this thing is eta, So you get L transpose eta L, which is eta. So L bar L also is a Lorenz transformation matrix. So the composition of two Poincare transformations, one after the other, is this particular Poincare transformation. This particular form is going to be very, very important in what's going to follow. This actually just goes to show closure, that is, two successive Poincare transformations carried out one after the other is a single Poincare transformation. In order to show that Poincare transformations form a group, we actually need to show the other properties as well. Associativity, we don't really have to check, because here, as in the previous case when we saw this, what we are doing is we are transforming coordinates, and the product rule for group elements is nothing but do one transformation after the other. For such things, as we explained before in the previous lecture, associativity is trivial. What about identity? Well, identity of course would mean that x prime mu is the same as x mu. That would follow if you were to take the lambda matrix to be nothing but the 4x4 identity matrix and the translation vector to be 0. So I'm not going to write I for any longer, that's to be understood from the context. I comma 0 is actually the identity. Of course, you should check whether the identity satisfies the basic property of the Lorenz matrices, but I transpose eta I is obviously eta, so that's sort of a given. What about inverse? Well, if x prime equals lambda x plus a, it's easy to see that lambda x is x prime minus a. And now, note that the matrix corresponding to lambda has determinant either plus 1 or minus 1, which means it definitely is not 0. So, this lambda is always invertible. So, x can be given by lambda inverse x prime minus a, that is lambda inverse x prime minus lambda inverse a. So, lambda inverse minus lambda inverse a are the parameters that you need for the inverse Poincare transformation, the inverse of lambda comma a, or when you're talking of this thing acting on states, this is actually the inverse of T lambda A. So all four basic properties, closure, associativity, existence of identity, and existence of inverse, has been demonstrated for this. So we would be fully justified in calling this the Poincare group. Now the Poincare group has several very, very important subgroups. One of the obvious subgroups that you have is basically the group of translations. That is, remember, the Poincare transformation is x goes to x prime equal to lambda x plus a. If you have lambda equals identity, which is of course a genuine Lorenz transformation, then you end up with x prime equals x plus a, just a translation of coordinates. And it's very easy to see that the composition rule in this case for two such translations, one a bar preceded by t identity a, that is two translations, first by a then by a bar, by either by appealing to the basic property of translations or by specializing the general formula that we had for the composition rule for Poincare transformations, we would see that this is T of identity a bar plus a. So this set of all transformations of the form TIA, this is the translation subgroup. It's obviously an abelian group with addition of parameters being the composition rule. What about the other scenario where there is no translation? So basically, if you are talking of only a pure Lorenz transformation with zero translation, well, If you carry out two such transformations one after the other, it's easy to see that this is also a transformation of exactly the same form, T of lambda bar lambda comma 0. So only Lorenz transformations form a group in its own right, another subgroup of the Poincare group, and this of course is called the Lorenz group. This group is not abelian because lambda bar lambda and lambda lambda bar might very well end up being two different transformation matrices. Well, some people call the Poincare group the inhomogeneous Lorenz group, inhomogeneous because of the extra translation, and according to that nomenclature, this would be called the homogeneous Lorenz group as well. But now remember, the Lorenz group, the Lorenz matrix has certain restrictions. Det L or det of lambda, whatever you call it, is either plus or minus 1, and the 0,0th element is either greater than or equal to plus 1 or less than or equal to minus 1. Now it's rather obvious that if you pick only those Lorenz transformations for which det L equals plus 1, then you do have a subgroup. Two matrices, each with determinant plus 1, will, when multiplied, give a matrix with determinant plus 1. So this thing is closed under multiplication or closed under composition, and you can easily check that the other properties for the group also works. So det L equal to plus 1, if you were to restrict it that way, would give you a subgroup. What is slightly more complicated to see is the following. If you were to just include only lambda 0, 0 greater than or equal to plus 1, and you take two such transformations one after the other, lambda bar 0, 0 is greater than or equal to plus 1 and lambda 0, 0 is greater than or equal to plus 1, then it takes a bit more algebra to show that lambda bar lambda, the product matrix, is also going to have a 0, 0 component which is greater than or equal to plus 1, and thus this also divides up our homogeneous Lorenz group into two distinct pieces, and this particular piece does form a subgroup. Our next result will take a bit more algebra to establish. But first recall that we have already proven that lambda 0, 0 for any given Lorenz transformation has only two possibilities. It's either greater than or equal to plus 1 or less than or equal to minus 1. If we now confine ourselves to those Lorenz transformations for which lambda 0, 0 is greater than or equal to plus 1, these are called orthochronous Lorenz transformations. Then we can establish the following result. If we take two such Lorenz transformations, lambda bar and lambda, and multiply them together, that is, find out the corresponding Lorenz transformation to applying one transformation after the other, it's obvious from standard matrix algebra that lambda bar lambda 0, 0 element is given by lambda bar 0, 0 lambda 0, 0 plus lambda bar 0, 1 lambda 1, 0 plus lambda bar 0, 2 lambda 2, 0 plus lambda bar 0, 3 lambda 3, 0. Now, if you recall the proof that we gave of this inequality, what we had done was used eta mu nu lambda mu rho lambda nu sigma equals eta rho sigma, the standard property which all Lorenz matrix elements must satisfy, and choose to use rho equal to sigma equal to 0 here. This immediately gives rise to the result lambda 0, 0 whole square equals 1 plus sum over I equals 1 to 3, 1 to 3, so of lambda I0 whole square. In addition to this, we could also use the analogous result which we have already established, that eta upper mu nu lambda rho mu lambda nu sigma nu would be eta rho sigma. And this, again with rho equal to sigma equal to 0, will give you lambda 0, 0 whole square equals 1 plus sigma I equal to 1 to 3 lambda 0 I whole square. Now the reason why I am focusing back onto this derivation is, if you look at the numbers here, you would realize that if I were to define a vector, let's say lambda vector, that's just a notation, to be consisting of these three numbers, lambda 1, 0, lambda 2, 0, and lambda 3, 0, then what this equation actually tells you is that the length of lambda vector is square root of lambda 0, 0 whole square minus 1. And very similarly, if we define a lambda bar vector by lambda 0, 1, lambda 0, 2, lambda 0, 3, then the second equation here applied for the Lorenz transformation lambda bar gives us the result that lambda bar vector's magnitude is square root of lambda 0, 0 whole square minus 1, lambda bar 0, 0 whole square minus 1. So notice that our expression for lambda bar lambda 0, 0 component essentially has lambda bar 0, 0, lambda 0, 0 plus what you can easily see is the dot product of lambda vector with lambda bar vector. Now the smallest possible value that this dot product can take is nothing but minus magnitude of lambda times magnitude of lambda bar. So lambda bar lambda 0, 0 component, the smallest value of that has to be lambda 0, 0, lambda 0, 0 plus the smallest magnitude of the dot product, which is minus square root of lambda 0, 0 whole square minus 1 times lambda bar 0, 0 whole square minus 1. So this is what lambda bar lambda 0, 0 component has to be greater than or at worst equal to. Remember, what you had here was a dot product. I have just replaced it by minimum possible value. That's why you have a greater than equal to sign here. Now the question is this number 1 or more? Frankly, I don't even need to check all that. All I need to check is the right hand side positive or not? Now it's obvious that this number and this number are less than the corresponding numbers here. So this is definitely positive. But remember, lambda bar lambda is a Lorenz transformation. So the only thing that is left, only possibility that is left, is that lambda bar lambda 0, 0 component must be greater than or equal to plus 1, because we know it's positive. Remember, there are only two choices. It's either greater than or equal to plus 1 or less than or equal to minus 1. Since this number is definitely positive, it has to be greater than or equal to plus 1. Hence, what we have established is, if lambda bar and lambda are both orthochronous Lorenz transformations, then so is their product. You can easily show that the other group properties also follow. And therefore, the set of all orthochronous Lorenz transformations form a subgroup of the set of homogeneous Lorenz transformations. In fact, the subgroup which is of greatest importance in this case is called the set of proper orthochronous Lorenz transformations. So this is a Lorenz transformation. So corresponding to x prime mu equals lambda mu nu x nu, with lambda mu nu obeying eta mu nu lambda mu rho lambda nu sigma equals eta rho sigma. But with the additional properties, the det of the L, where L is the matrix made out of lambda mu rho, is plus 1, and the 0, 0 component is greater than or equal to plus 1. This is a subgroup of the Lorenz transformations. There is a subset to which the identity belongs. Note that any Lorenz transformation that can be obtained from the identity by a continuous change of parameters must have determinant of L equals plus 1. Remember, you're changing the transformation continuously, so its determinant can only change continuously. Since the only possible values are plus 1 and minus 1, any change would have to be discontinuous. So since you're starting at plus 1, you'll stay at plus 1. And similarly, any such transformation starts at the identity which has lambda 0, 0 equal to plus 1. And since the only possibility is lambda 0, 0 is either bigger than plus 1 or less than minus 1 with a big gap in between, continuously changing parameters cannot change something which started at plus 1 to something which has become negative. So for all such transformations, lambda 0, 0 has to be greater than or equal to plus 1. So the proper orthochronous Lorenz transformations is precisely that subgroup of Lorenz transformations which can be reached from the identity by a continuous change of parameters. Indeed, any given Lorenz transformation is either proper orthochronous or the product of a proper orthochronous transformation with one of three possible matrices. One of them is the matrix P, another one is T, the third one is PT. Well, P is a Lorenz transformation in the strict sense because it keeps the interval invariant. It's actually called the Parity Transformation, and mathematically speaking, if you think of parity as an operation, the corresponding matrix is diagonal and has P00 equal to plus 1, no change in the temporal coordinates, P11 equal to P22 equal to P33 equals minus 1. So parity, of course, is the operation which reverses the sign of spatial coordinates. T, on the other hand, is time reversal, and what that does is it changes the time component. So T00 is minus 1, T11, T12, T22, T33 are all plus 1. Of course, all the other off-diagonal elements for both the cases are 0. PT, of course, is just a product of these two, which means PT reverses the sign of all the four coordinates. So PT's 0, 0, 1, 1, 2, 2 and 3, 3 components are all minus 1. And of course, all the off-diagonal terms are 0. Now, the transformations T of lambda A induce on our Hilbert space a unitary representation or a unitary operator U of lambda A. That is, a state psi in the Hilbert space will change to U of lambda A psi under a Lorenz transformation. Now we expect these U of lambda A's to mimic the group property, and for the time being, we are going to assume that we will have genuine representations and not projective representations here. So, U of lambda bar A times U of lambda A, which of course means you carry out this Lorenz transformation T of lambda A first, then you carry T of lambda bar A bar out, and the resulting transformation on Hilbert space is going to be given by U corresponding to the product Poincare transformation U lambda bar lambda, comma lambda bar A plus A bar. We will see, as a consequence of this particular demand, we can make a lot of predictions about the way in which the infinitesimal generators of this transformation commute among each other. In particular, we will be able to work out commutation relations for the 4-dimensional logs of angular momentum as well as momentum. That is what we are going to do next.